Okay, so let's do some basic review of the work energy theorem and then move into other forms of energy. So remember that energy, we've given it this sort of like working definition of the ability to do stuff. And that's about as good a definition as there really is. In this case, doing stuff can be broken down further into the ability to exert a force. So, in order to cause something to accelerate over a displacement. And that is what we call work. So, that's work. Yay. So, work is a force applied over a displacement, but more importantly, in this case, the force has to be the cause of the displacement. So, for example, if a hockey puck is sliding across a horizontal frictionless ice surface, there's a weight force pulling the puck down and a normal force pushing the puck up. But because those forces are not causing the puck to move across the surface, they're not doing work on the puck itself. And that should be clear because the puck, if it slides across the surface at constant speed, it's not changing in its ability to do stuff. It's not changing its energy, and therefore there should be no work being done on it. So, how we represent that is with cosine theta. And cosine theta represents this force causing the displacement, where theta is the angle between F and delta X. So that theta right there, cosine theta, that is what shows the force causing the displacement. The other way we can represent this is with work equals the dot product of force and displacement. And dot product here means the same thing as this cosine theta does. Basically, dot product is times cosine theta of the angle between the two vectors. It finds the product of the parallel components of the vectors. So dot product and times cosine theta are effectively the same thing. Remember too that when we have this sort of algebraic version of work that we've represented here, that's only true for constant force, uniform forces. When we have non-uniform forces, we have to use our calculus here. So in that case, work would be the integral of force with respect to displacement from an initial displacement of x equals x naught and a final displacement of x. So that's the calculus way. This is for non-uniform force. Or the alternative way to do non-uniform force is work is the area under a force displacement graph. Apologies for the yard work sounds. Apparently, my neighbor's choosing right now to leaf blow, which is definitely non-essential and definitely still happening in my neighborhood. Anyways, so that's our work stuff here. Now, how does this pertain to actual energy? Well, when you have a force that causes an object to actually be displaced, it's going to start to move. And that movement gives it the ability to exert forces on other things. So, for example, like a moving bowling ball can knock over bowling pins, but a stationary bowling ball cannot knock over bowling pins. That moving energy, the ability to do stuff because of movement, is called kinetic energy. And that is usually abbreviated by a K or KE. And so that kinetic energy is energy of a moving object. Now, what does that have to do with work? Well, work is what causes that object to gain the energy to move. So in this case, let's see if we can derive a formula for kinetic energy. Work is the integral of force with respect to displacement. Well, force is mass times acceleration. So then work would be the integral of mass times acceleration dx. Assuming that that mass stays constant, then we can factor it out of that integral. So that would be work equals mass times the integral of a dx. So moving this along, we also know that acceleration can be represented in terms of calculus as well. Work is mass times the integral of, instead of acceleration, we could call this dv over dt. And the reason we can do that is that acceleration is the derivative of velocity with respect to time. Using the chain rule, I can sort of manipulate this further. I could represent this as dv over dx times dx over dt times dx. And the reason I can do that is that ultimately this is algebraically equivalent, right? Because these two dx's would cancel and I'd end up with the same expression. But the reason that's significant is that if we look at this now, we see, work could be represented as the m times the integral of dx over dt times dv. So that's just, again, sort of manipulating and simplifying, but ultimately this is the same expression, right? Well, what is dx over dt? The derivative of position with respect to time is velocity. So then this simplifies to m equals the integral of v dv. Aha! Well, that is very easy to integrate. That means that work is m times v squared over 2. Or work is 1/2 mv squared, where v is the velocity. This is the work energy theorem, because this is work done being equivalent to moving energy. That work is equal to kinetic energy gain, therefore Ke must be equal to 1/2 mv squared. And this is our formula for kinetic energy right here. This is the one that we're going to be using all the time to figure out what is the energy of a moving object. It's 1/2 times the object's mass times the object's velocity squared. And this can be solved for algebraically as well, but because we're in AP Physics C, we're going to do it using calculus.